So I'm Will. I've been around protocol labs for the last few years, so thinking about Filecoin, and I run part of our privacy research in that space. And before this, I've mostly been in academia doing distributed systems and networking, and so looking at how people get access to the internet and measuring the interruptions and censorship events that happen online, so looking at sort of that adversarial network environment. And this is a talk talking about the state of primitives at the network level. To ground what we're talking about here, there is an anonymity trilemma that came out a bit ago that's sort of saying you can't get good anonymity without giving up something. And so this is this trade-off of like, am I going to lose performance? What am I having to give up in order to get better user privacy? And you can break it down a little bit, which is when you're thinking about what are you giving up, you either are giving up some speed, some latency, some like really fast communication, or you're going to give up some efficiency of do I have to buffer, do I have to say extra things? Right? If I'm willing to send a bunch of messages with my real one in it, I can still do that quickly. And so breaking this down into sort of, what do we actually mean when we're talking about these system designs that give me levels of privacy starts to give us a more nuanced way to think about how do we add stronger network privacy and communication privacy components into systems. The other thing that you need to think about is what is the adversarial network and the adversary that communication is designed to protect against. When you look at things like zero-knowledge proofs, you're looking at the communications themselves, right? Of someone is looking at this message, and it's that they can't then figure out other things beyond what the proof is about. And so you end up framing it in something that is a similar sense to the sorts of problems that you might solve with end-to-end encryption, right? That you don't want to be able to look in and understand what the contents of a message are. End-to-end encryption means only the destination can see that, whereas zero-knowledge means everyone can see the one thing but can't see other parts of what went into a message. But you've got this sort of additional part of the communication. If I'm sending my zero-knowledge proof every time I get a message from someone, watching when I send it is still revealing stuff about the fact that that communication is happening in response. So the patterns of when messages are sent, which contracts or which other endpoints I'm interacting with, these are all leaking metadata. And so you need to think about what that sort of scope around the communication you're worried about and define that. In the network context, it ends up being things like global passive adversaries, which are a description of something like a government power that can sort of tap in and look at the various links and points of the network and potentially observe all of the different messages in your system that get used as the threat model most commonly, because it's a relatively easy one to describe, and it gives you an adversary model to work around. So positioning this, right? You've got your contents of your message between two participants, and that's where we have end-to-end encryption. But the things that I think are more interesting is the stuff around it. And the main ones that we talk about there is the two participants, the from and the to, how big these messages are, and when they are being sent, right? Because I can look at a lot of the social network graph of who's talking with whom, and I can look at, all of these messages have been really small, and suddenly here's a big one. Who sent the picture? Probably the person who sent the big one, right? The size of messages in relation to the content can end up leaking a lot of stuff. Okay, so how do we start to reason about this a little bit? When you're trying to build your system and you're saying, is this effective at this adversary or in this model? What building blocks do I want? You also need a metric of being able to say, this is better than this. And when you've got this very high-dimensional thing of like, well, there's this attack and there's this attack, you need to somehow collapse that down to be able to say better. And so you need a metric. And there's 2 to 3 metrics that get used most commonly. One is k-anonymity. And so k-anonymity is a measure of privacy of saying how many other people could this be, right? I send a message. I've tried to hide who that message is to, but is it going to a pool where there's 10 other people that read it versus a pool where there's 100 other people that read it, right? And so by looking at how many potential recipients or how many potential options there are that I've masked, a larger number probably is more private. There's a bigger set. And so that's one metric that gets used. And there's a set of contexts where that is like a very naturally aligned way to be talking about, what is a better privacy. There's a concept of linkability. So you've got a message, and an adversary wants to say, I think that this, is a message from Alice to Bob. And you can say, how much better than a random guess can that adversary do, given the information it has? And that gives you a sort of a quantifiable way to talk about how linkable versus unlinked versus anonymous is this. Is the ability of the adversary, based on their knowledge, purely a coin flip, like it's as much as a random guess, or how much information is leaked in each message. And so that is another quantification of this metric of privacy that gets used. And the final one is indistinguishability. And so this is now looking more at data. This gets used in things like differential privacy, where you've got a statistical distribution of all of your data, and you sort of look at how much you need to change the values to be able to individually identify a message. And so you're looking in your data set, how much does this message or this piece of data stand out? How much would I need to modify it to make it go back to sort of my norm or into my statistical, 1 sigma out from my distribution? So you're looking at how different from the rest of the data set or the normal position of the data set an individual entry is. And that gives you a sense of, okay, all of these messages really are exactly the same size, and so you aren't learning anything, versus, well, okay, the messages are all different sizes, but they're all sort of uniformly distributed, and from any individual message, you're not really learning much. So there's this concept of sort of approaching it from this statistical position. So we've got metrics for how good we are. We've got a basic sort of like framing within the concept of someone watching the network communication. And so then we can get to these building blocks of what do we do to do better. There's 3 or 4 that are getting used or that are at various levels of deployment that are relevant here. And I'll sort of give sort of quick senses of where each of these are and how quickly they're moving. Mixed nets are getting used a fair amount. There's a couple examples even at this conference. And so this is saying we're going to take our communications and we're going to send it through a few intermediate nodes before we deliver it to the recipient. And those nodes will each sort of reshuffle groups of or batches of messages. And so if at least one of those nodes in the process is not colluding with the others, at the end, all of these messages that are in a batch get sort of mixed together, and you can't tell which sender sent which message. So you unlink the origins and the recipients of the batch of messages that come together. There's a set of techniques that have been used around padding. So you've got messages that are different size, where if you just encrypt your messages, you still can distinguish between the images or the length of the web pages, right? The Google homepage is a very specific size. Even if I end-to-end encrypt that, it's clear that I've gone to Google versus I've gone to some other website. And for many types of messages, you can end-to-end encrypt, but you can still fingerprint specific types of communication because of a known size. So how you add padding to reduce that ability of someone who's watching the network to understand what specific types of messages and flag things. Multi-party communication is a sharding that gets used to most commonly take keys and allow a group of participants to do operations in regards to those keys without individuals having full control of the key. And so you can do things like re-encryption, where an encrypted message can get transformed to a destination later without the people controlling the original private key being able to see that message. And so it's a primitive that gives us another point of flexibility in a way that's fairly computationally practical in many cases today. And so we're starting to see that deployed in a bunch of decentralized systems as, I don't know if I want to say a stopgap, but it's a technique that works in a federated mechanism where you're not going to something that's fully decentralized, but you get something that is very practical in terms of what it can do today. And then I think one of the areas that's getting more attention is homomorphic encryption, which is sort of more general computation over encrypted data. And one of the specific constructions or problems that you can do with homomorphic encryption that's starting to get deployed is a construction called private information retrieval, which is how do I access an item in a database without the centralized server that controls the database knowing which item I'm asking for. And that can be used for a variety of subsequent Web2-like interactions, adding privacy, where it reduces your trust in a relay, the person who's the wallet provider looking up balances, and has a bunch of relevance for different decentralized things where you may want to have a gateway or a relay without putting too much trust or giving them too much ability to observe what's happening. Okay, so let's talk through these a little bit more. So back to mixed nets. Mixed nets started really early. Even in the 80s around email, there were a set of mixed nets that would provide anonymous email. And these would typically work initially on a fixed batch. And we're using k-anonymity to talk about what sort of privacy they were giving. So they would wait for 100 emails to get sent into the mix to an entry. That would shuffle them, send them to a second, send them to a third, and then send them to the destinations. And so you would be able to say, all of the emails being sent through this have a k-anonymity level of 100. You are mixed with 99 other emails, and so for each email that gets sent, it could be any of the 100 senders as far as anyone else can tell. There's a couple downsides that subsequent decades have been able to improve on here. And so as we look at Lupix, which is what NIM is based on, and a bunch of modern constructions, they're doing a couple statistical tricks or things to try and be able to provide better performance and better security. And so the sort of interesting thing that comes up in a couple contexts here is that you'll use an exponential decay of when you of how long you hold things or when you send them out as one of these mixes. So here's one of the early privacy systems description of this part of the process. And this property is also called like historylessness, which is if you use a Poisson or an exponential decay distribution of how long you're holding it. So most commonly you'll hold it for 1 second or 2 seconds, but there's that probability is an exponential of tail off of you might hold it much longer. And so you can't know when something is being sent out if it's been held for a really long time versus it's probably been held for a relatively short time. And so the interesting thing here is that you never quite know, and so there's this probability that builds up of uncertainty from the point of view of the attacker, where while it's likely that that a message being sent out is from sort of the recent batch that's getting mixed, they end up with a lot of complexity of having to still have the probability that any individual message getting sent out could have been from quite a long time ago. And that makes their lives quite a bit harder in terms of they now have to do a very probabilistic reasoning about it. And it gives you the ability to inject a set of sort of false messages that could well be mixed. So there's a couple things here. It also is nice because if clients are sending it, you can't ever tell if a client is offline or is just in one of the bad exponential decays, right? Like, I probably should have checked in with the server again in the next 5 minutes. But if I got unlucky on my coin flip and decided that the next time I check in is 2 hours, you can't tell if I close my laptop or if it's that. So these exponential decays give you a set of unlinking between your activity and the actual sort of like regular frequency communication of messages that helps remove certainty about online or certainty about mixed sizes. Pond was a command line, although I think there was a Linux GUI communication system that Adam Langley had a decade ago that was doing a bunch of interesting both padding and communication frequency proof of concepts in this space. So padding, one of the common ones for systems that want this is you just say everything is going to end up being a constant size. We're just going to say every message I send is 4K. And if I have a larger message, I'm going to chunk it and I'm going to send it as multiple messages. That is a quantization, right? Every message is 4K. Now you have to look at how many messages I send and you get a multiple of 4K, but that's better than getting exact byte sizes. I've meant that you get less information. There's been sort of specific research projects looking at types of data. So like if it's web browsing, what is the right level of these message sizes that start to make it hard for you to know which websites I visited just based on sizes? How do I quantize that enough and put enough padding that you can't tell if I'm looking at Google versus something else? Once you go from a closed model to an open model, and what this is like, do I know all of the messages that might be sent versus is it user generated where I don't know? So if you're looking at like chain messages where there's a smart contract with a set of potential methods or inputs, and so there's going to be a fixed set of sizes, you've got a much harder problem because it's much easier for an adversary to identify which of those methods something is, even if they're pretty encrypted, versus there's a lot of web pages. And so the actual question someone is asking as soon as it gets to user-generated content or the web or one of these open things is it in my set of known fingerprints or is it not? And that's a harder thing because the not could be anything. The web page sort of like what we feel is safe level that the CS Buffalo paper ended up talking about was for web browsing, you could say, when I am sending a web page, I will either just keep spewing bytes in quantizations of a quarter second, or I will be silent for the quarter second. And that was, and just sort of saying I'm either going to be sending at full blast or I'm not going to be sending, was a sufficient quantization to make it very difficult to understand web browsing patterns, with the caveat that it was sending a whole lot of extraneous data and padding data that wasn't relevant. So you were getting a lot of bandwidth cost, but you had very much hidden what the actual underlying communication pattern was. Okay, mixed nets, DC nets or MPC. So multi-party communication, probably one of the earliest conceptualizations of this was dining cryptographers from Chom, where you wanted a set of participants to be able to jointly calculate a value without knowing which individual had contributed which sort of sub-value into it. Can you calculate the total bill without knowing the individual people's portions of it, things of this nature. And this same sort of type of communication system of trying to get to a group consensus outcome without knowing the individual participants' portions is the same building block that's getting used in a lot of MPC today. The relevant constraint here to be thinking about in employing this as a building block or thinking about it is the size of your group ends up having scale issues. And so you can have an MPC group in these more generalized things that goes up to maybe 100-ish or order of hundreds. But if you're trying to say you want a really broad group with thousands or millions of participants that you're trying to sort of aggregate up, you're either going to end up with like a tiered approach, or you're going to need a much more specific construction that generalized mixed nets or distributed key generation or things that happen in this framework. It's the communication process of the group aggregation that ends up scaling in bad ways. And so that's been a lot of limitation in applying it, especially in decentralized contexts, where if you want this to have the same sort of like, this is permissionless and decentralized, like a full chain or something like that, you end up sort of staring at the potential of thousands of participants and getting scared that things will stop working efficiently. And so you end up needing much smaller validator committees or other techniques to limit the potential scale of these aggregations. Cool. I will end with this building block and description of where things are with private information retrieval, which is most commonly being constructed these days within a homomorphic encryption framework. So the problem is, how do we query a central database without revealing which item I'm asking for? The straw man to help convince yourself that this is a reasonable problem to even ask in the first place is I could ask the server, hey server who has the database, give me your whole database, and then I can locally grab the item I want out of it. And the server doesn't know which item I'm interested in. So now it's just an efficiency problem of, can I do that without having to get the whole database? Can I reduce how much network inefficiency I've introduced? Luckily, both with and without homomorphic encryption, the answer is yes. This is great formatting. There's an information theoretic construction which uses multiple servers and ends up being computationally fairly efficient, but you again end up with sort of like a committee trust at least one not to collude style model for your servers. And that's sort of been demonstrated for thousands of queries per second, 10 gigs or so of database size. And then the homomorphic encryption is, in general, about an order of magnitude slower, but only needs one server. I think this probably, I need to update, although we don't have great numbers, but there's been advances in the last, even this summer, that are probably 1 to 2 orders of magnitude larger data sets than what's shown here in this homomorphic one. And I'll get to that in a minute. Recent things that have happened, there's some work from the end of 2022 called Spiral that showed how to efficiently take all Bitcoin and Ethereum wallet balances and let you query current balances without revealing which account you were after. And so you can think about this in the context of an RPC gateway or the wallet provider for a MetaMask or a Brave wallet or something, where you can not be revealing to the server who you are as you're asking for things like balance, which has reasonable privacy implications. There's a whole set of like, how do you really productionize these systems in things like, are you going to also authenticate that you're a valid user as you're doing these? And how do you do that without leaking? And does that lead to inefficiencies? And these are all 1 or 2 orders of magnitude of additional cost so far. They're getting a little bit better. They've basically kept up with the performance increases that are happening in the homomorphic encryption constructions, but they're still sort of additional cost beyond what a proof of concept is going to be able to get to. The like exciting thing that happened this summer was Apple has rolled out a Swift framework, but more importantly, all iPhone users, when they're doing caller ID lookups, are going to be doing it through a homomorphic PIR query, where they're not revealing to Apple which phone number they're interested in. So you can think of the set of all phone numbers is pretty big, and in particular, the set of phone numbers with the resulting caller ID name and probably more important for database size, like the little picture you get of the user, which is now going to be some kilobytes per entry, means that you're probably much more than 10 gigs of database size that they're doing this homomorphic PIR query against every time someone's getting a phone call. Which is cool, right? They've gotten this to scale enough that they're actually feeling comfortable deploying this. It's able to work in the same, order of 10 to 100 milliseconds that you would expect for a Web2 centralized API response, but you have to trust the server quite a bit less. So that's a exciting place to be. There was a workshop, and this is, I guess, my involvement in this one is helping around some of this workshop stuff. But we did this at PETS last month. There's going to be more at Usenix Security, and the work in this homomorphic encryption private information retrieval space seems to be continuing, which is exciting. I'm happy to answer any questions, probably not on stage, but come find me after, around how to apply these and how to think about the network privacy implications and properties of decentralized systems. So feel free to find me. Great to talk.